Okay, so then we will start with today's lecture. Before I start with that, I hope it went well yesterday with the exercise and that you could run FECO. And for the few of you who didn't or couldn't run it during the class, I hope you've been able to do it afterwards, and that the VPN and the connection has been resolved for those who couldn't come to the 41, 18, and 19 rooms. So the best thing is, of course, that if you can run it remotely from home, but if you cannot do that, you're also welcome to those rooms where we have the computers. And you also see now that questioning hours have come up for the lab. So the first one is tomorrow, Friday, and then there are some hours on, I think, Tuesday, and then maybe Thursday, Friday next week. And that will be the deadline for handling in the first part of your lab, which is the design of your 2 patch antennas. So you have 1 week to do that part. Any questions about the course or the lab so far?
Excuse me, Mats.
Yeah.
Actually, yesterday I was very excited to listening to for you when you catches our attention for many points in the lab.
Yeah.
So if you can continue with that, if you can, I suggest to make one lecture in order to share your comments on the results and catch our attention for many points in order to increase our understanding in the lab or in the results.
Okay, so I'm not entirely 100% sure what you mean. Is it about the discussion about the simulations that you get out from FECO and the interpretations of the results?
Yes.
Yeah, so a very good time and place to do that is, for example, during the exercise classes. So the same as we had yesterday, we will have one next week. And in all of those, I would say, bring up everything with simulations, with paper and pen, and I try to explain it the best way I can. So that's a really good opportunity to ask all of those type of questions. And I think that will be a good opportunity for you to do it. So if you have simulation, you see results from both your patches and dipoles and so on, just bring it up. Share your screen and I try to explain it to you the best way I can. So that's a very good proposal, and I think we can run it in these exercises in some ways. Okay, so that means that we will start with today's lecture. And what we will do today is that we will now accelerate the amount of antennas. So you've seen so far in the course, we had the dipole. We took quite 2 weeks about the dipole, and then it came the patch antenna. And now we will have loop, helix, and spiral antennas. So we will just increasing the number of antennas. Next week, we will take a short break from that and actually look at array antennas, because then we will put these elements into use into arrays. And then we will continue with horn antennas, reflector antennas, and so on until the end of the course. Okay, so what we will do today is to then look through this type of antennas. The main part here is actually about the loop antenna. And the loop antenna can be seen as the magnetic counterpart of this dipole antenna that we've been looking at. So we will start with what is the small loop antennas, and that is similar to the Hertzian dipole. This will be the Hertzian magnetic dipole. So they are the fundamental building block that we have to understand the radiation and properties of many type of antennas. We will also see what's happening when we make it larger, look at large antennas, and we will actually see that these large loops is very similar to the folded dipole that we already looked at. And then we will use everything we know here from loop antennas and actually dipole antennas to study what's called helix antennas, the 2 version axial helix and a normal mode helix. And then in the end, we will go to called a spiral antenna, which can be considered as another version of the loop antenna where we add many loops in a slightly different way in the helix. So that's a family of antennas we will look at, and we will try to understand their impedance properties and radiation properties. That's the same for all type of antennas. So let's just take a loop. And this is now something that you can simulate yourself in FECO. There are codes or setups for a loop. So we will consider here the geometry that you can see up here. So we say that the diameter of this loop is 2a, so the radius is a. And then we have a wire radius here, which is very small, which is this b. So think about this as you had the dipole, that was like a long thing going just up like this with very thin wire. Now you take and close that wire into a loop. So same type of antenna in some ways. And the scaling of this one that I write here, Ka, that is then equal to c over lambda, where c is the circumference of these ones. So the way when you go around all the way around the loop. And that is, of course, 2 pi times the radius that you have here. And that means that Ka, so K, the wave number times the radius, is the same as a circumference over lambda for this case. It's just to get some physical understanding of the properties. And then what we have plotted here is then the input impedance of this. So this you could say it's like data from FECO or another software that just simulates these ones. And now we should first look at that one and try to understand what we can see, and then we will understand actually why this is happening in it. So if we look at the radiation resistance to start with, that is the blue curve that comes here. And what you can see there is that when the size is very small, so it's sub-wavelengths going around it, the radiation resistance is very, very low, almost no radiation resistance. And then it's peaking up here, and then it goes down again, and then it comes to a point where it is 1 wavelength, and then it has maybe a better number in some ways, and then it starts oscillating a little bit. If we look at the reactance, then we see something coming up here, almost as a straight line in the beginning, and then coming up top, falling down, and then coming in here again, and then it hits 0 around 1, so Ka1, or 1 wavelength going around it, and that is the resonance that we will use. And then it starts oscillating again when we come up here. So if you think that, and now you compare it to what you remember from the dipole, you can see it's very different. The dipole in some ways went down here very low as capacitive in the beginning, and then eventually it hits a resonance frequency, and then that resonance frequency at half a wavelength, that's where you used it. That was a capacitive antenna. And this one is instead inductive. So you can see for low frequencies, long wavelengths, it doesn't behave as a capacitor, it behaves as an inductor. I hope that doesn't surprise you, because the loop here, of course, is that it can have a current just going around here. And that is really an inductor. So it should behave as an inductor. That is the electrical component of an inductor. And that is what we see in that cases. And then we see things that are maybe slightly harder directly to interpret. But we're going to try to interpret that to explain what we actually see in this loop antenna. So what I just mentioned there is that for low frequencies, it's inductive, and the radiation resistance is really low. We will actually calculate it very soon. There is an anti-resonance at half Ka 0.5, or the circumference is half a wavelength. So there it doesn't work. You might remember that from the folded dipole, because it behaved a little bit similar. The shape is a little bit similar for that. And then you have the good part, which is this resonant, approximately at 1 wavelength. And again, the same as the dipole. The half wavelength dipole is not holy. It's a good rule of thumb. A 1 wavelength loop is not holy either, but it's a good rule of thumb. And if you look carefully here, you can actually see it's not precisely at 1. It's slightly shifted from 1, and that's fine. There's no problem with that. But it's a good approximation to understand that that's around 1 wavelength going around it. That's where you have your resonance. And then you can tweak it a little bit. So what we will do today is really to look at this loop antenna to start with, and analyze it in two regions. So we have one region here, which I call small loops, and I have another one here, which I call large loops. And small and large is now always related to the wavelengths. So the antenna here could, of course, be 1 meter, it could be 100 meters or 1 centimeter. It doesn't really say large and small. It is in relationship to the wavelengths. So this is what's called electrically small. So it's much smaller than the wavelengths. And the large one now is not many wavelengths, but it's still called large loop in these cases. It's just one wavelength in these cases. So those are the distinction that we will look at. That is the places where we try to understand the radiation and the properties from this loop antenna. So let's take another one where we then also show the radiation pattern. So this is also typical simulation. You can just run directly in FECO. There are the codes to do it. You will get out here the input impedance, and then you will get out some radiation patterns. These are the directivities. And in this case, the directivity is now taken from 2 points. One is down here, and the other one is at 1, which is here. So one is it's in this region where it's small, and the other one is in the region where it's large. And just looking here at the radiation patterns, this one and this one, you can really see that they are very different. The radiation is completely different in these two different regimes. The behavior is very different. And if we want to try to understand this, we of course need to analyze it and try to go into the details of what's happening. But before we do that, and before we look into this one in detail, if you look at this small loop here, and you see the radiation pattern, do you recognize the radiation pattern? I hope all of you is shouting out yes, because this is your donut that you had from the dipole. You can really see that the shape is the same. So this one radiates a lot of power here in the X and Y plane. So in the horizontal plane, there is a lot of radiation. When you look a little bit up here, it radiates much less. So much less radiation up, and basically no radiation when you go in the Z axis, so in the vertical direction. Exactly the same as you had from the dipole, the small electric dipole antenna. Precisely the same. You can see that the values here are also very similar. We calculated this 3/2, 1.5. Very much what we get here. Okay, 1.47. So it's a good value that we get out. And now when you look at the next one, the larger one, what does this look like? That doesn't really look like many things that we have seen, or does it? Have you seen that radiation pattern before? If you think, yes, good.
Yes.
Yeah. Where have you seen this radiation pattern?
And patch antenna.
Yeah. It's
Yes,
very similar to the patch.
And 2 dimensions here.
Yeah.
Yes.
And why could it be similar to what you saw from the patch antenna? Because now it's a loop antenna. It's definitely not a patch. And of course, when you do the patch, it is only the upper part. So this top part really looks like the patch antenna, which because the patch doesn't radiate below the ground plane. But what radiates above it is very similar to this. And how did we explain the radiation pattern from the patch antenna? What we did there is that we said that we had our patch, and we said that it was dominated by one dipole there and there when the feed was offset in this one. So it radiated as from 2 dipoles. We will soon see that this large loop antenna radiates as from 2 dipoles. But it, of course, radiates both up and down. But it will give a pattern that is fairly similar. And we can actually see that this is related to when we had the folded dipole, because then the folded dipole was just at this distance here, D, was very close to 0. And then they're radiating like a regular dipole. So it radiates like 2 dipoles actually. And this is what we're really going to understand with this. In the simulations here, it's again things that you could do. So just putting in now planar loop in this case, so instead of a wire, it's just a flat piece of metal that sits there. If we take out the circumference of this one, you can calculate it to 314 millimeters. We can go down and read off the resonance frequency. The resonance frequency is 1 gigahertz, which means that the wavelength is, of course, 30 centimeters, which is 300 millimeters, which is approximately the circumference. So the rule of thumb really works there. So there comes this resonance when it fits one wavelength inside of it. And if you think about your folded dipole, you know, this one, there we had this distance here, we said it should be half a wavelength dipole, it's lambda over 2, but there are 2 of them. So the circumference in these cases, which means that we go all the distance around these ones, is of course approximately lambda. So it's a similar behavior as a folded dipole, we can see. But we will now do this a little bit more in details. So we will start with a small loop. So in this very, very small loop, the dimensions is much smaller than the wavelengths. So if we feed this somewhere, there will not be a huge, what to say, phase shift over this structure because it's so small. So then we have to say what is the current in this one and what is the current density of this one. So you can see an animation up here where, or it's not, yeah, an animation of what the current density looks like. So of course it's going around the wire. So the current is following the wire and it's always going in the same direction. So it's just floating around the loop in this case, the wire that we have. And then I need to write down in some ways an equation for that, what that is. And we put it now to start within the XY plane. So Z is equal to 0. So the current density doesn't live outside the XY plane. And that I can use these delta Dirac functions again. Now you start remembering, now we're back to what we started with in this course, when we wrote up the dipole antenna and the radiation pattern for it. Then we had to write where is the current density of the dipole antenna. Now we do the same thing of the loop. The next thing that comes in is that, of course, this one lives here, and the wire here has some radius, and I call that radius A. And that means that the radius is always equal to A. Okay, I have to write that again in my current density. And then I can do again with one of those delta Diracs. I can say this one always lives at this distance A. So the first part here, this one say XY plane, and this one says where the radius is. And that means totally I actually get the current to go around this animation that we can see. Yeah. And then it has a direction, and that goes in this phi direction. So it's pointing always where this vector phi is pointing in these cases. And then it has an amplitude I0. So that is one way to write up this current density. And I put it in a coordinate system. This is what we just did. So I have it in the XY plane. I have the radius that comes out, and I have the direction here pointing in this phi hat direction that sits there, which is always along this y. So that is my current density. And then we have learned the procedure to determine the radiated field. We should take the Fourier transform of this one. So we should put them into this integral that at least looks like the Fourier transform. And we should compute what is that. And then we get the radiation vector. And when we have the radiation vector, we can get the electric and magnetic fields. So let's do this. And I will now warn you, this is slightly more complicated than for the dipole. But you can follow all the steps there. It will be slightly more complicated. So this is just what I explained where these pieces are coming from. And then, as I mentioned, we should determine the radiated field. We use the radiation vector. So basically the Fourier transform that we should get out of it. And then we need to plug in all of the things that we have here. So when we compute the radiation vector, of course, we have this R hat scalar product with R prime. So I have to take that and I have to write up what they are. And those we have in the formula sheet. So I can just plug it in what they are. I can take it from my description of the current density here. So the point to the source is always going out somewhere here in the direction, the radial direction for these ones. and then I have to multiply with the r hat that sits here. And r hat I have in the formulation. So this I can get together. If I simplify that, I can write this as this expression. That's it. So this is the phase term that we actually have that we have to evaluate. And if we now take this, we need to plug it in, and to calculate the radiation vector, one thing that actually simplifies this is that from the symmetry of this problem, we can realize it will only have a component which is in this phi direction. So it will move around in a spherical coordinate system, but it's only have one component which is in the phi. And I would say in these cases, trust me on that one. It's a little bit complicated to actually show that, but in some ways you can understand it because the current has that symmetry. It just moves around in the phi direction. So yeah, it's kind of reasonable that the field doesn't depend on other components. And here is the calculation. So I will do this little bit, just go through it so we can see what we are doing. And there is one approximation I will point out to you in these cases, because the important thing is that we will interpret this afterwards. So we start computing here the radiation vector, and we take only the phi component out of that one. And that means that the current density that we have wrote up, we can do the scalar product with that one. And that I can take from what I have on the previous slide, what I have written up what the current density is. And then I can add in to the next part of that, what was the phase factor. But before I do that, we should integrate this over all the volume. And when we plug in the current density, we have this good delta Diracs. So when we integrate over the delta Dirac, we get 1. So when I do the integration over rho, I only get the radius A. And when I integrate over Z, I only get 1. So those one disappears. And then we plug in what we have up here. It's a little bit mathematical in these cases, but I take this phase factor that we pulled out on the previous calculation, and that is what sits up there. So that was on the previous slide. And from this one, I have this cosine function that sits there. And this is now integrated over phi, and we can do realize that this is independent of phi, the results that comes out. You can always translate this. And then you get one integral left that you should compute. And this actually can be computed, but let's not do this in this course. We do a simplification of this because we have said that the loop is small, which means that we can take the exponent that we have here, this one, and we can write up that our e raised to x is 1 plus x in these cases. So we can use a Taylor expansion of the exponent and plug that in. If we plug that in, we get what it sits here, and then we can realize that we integrate the 1 over cosine phi, it's as much positive and negative, so it doesn't contribute. And then I can integrate the next piece, which is only over phi, and the end result is what we see down there. So I'm fully aware that probably the details of this calculation is very hard to follow on this kind of lecture, and that's fine. You are able to do it, but you need to sit down by paper and pen and do it yourself. The most important thing is the end results that comes out here. So if we take a look at this, what is it we got out in these cases? We got out here that our radiation vector there is equal to this thing here. That is what we got out. And the A that I have plugged in here is the cross-sectional area of the loop. And the fun thing with this is that it actually is the same for another shape too. It's not only for a circle. It's valid for other shapes too, but we don't do that in this course. I think I got a question here from Khalad. What happens with the cos function? Maybe you can point that out.
Cosine phi minus phi prime in the second line here in the middle.
You mean this part here?
Yes.
Yeah, so I replaced that with only cosine phi prime. And the reason I can do that is that I integrate this from 0 to 2 pi. So wherever I integrate that, you can think for a given value of phi, you just integrate from that value of phi and add 2 pi to that one. And it's irrespectively where you start at phi. So the result that you get out do not depend on phi. So you can translate that integral. Let's say like this, what I can do, I can introduce a new variable here, phi bis, which is equal to phi minus phi prime that I have. And if you do that variable substitution, you will see you have the same integral. So that is the step that I'm doing. I know in some pieces here I might move a little bit fast because it's also a lot of details, and those are not the most important ones in this case. But it is a variable substitution, you can see this. And of course I can do it without the variable substitution because I basically do it in my head in this case. So that is how that phi disappears. And if I take it in another point of this, imagine what you had here. You have a current that just moves around here. And what is the phi angle? That is where you sit in the x and y plane. So you have one phi there, another phi there, another phi there. And what you see is a loop. And of course you see the same loop from any direction of phi. So your result cannot depend on phi. In a similar way as when you had the dipole, you know, the dipole sticking up like this. Of course, the radiation is independent of phi from this one because it's symmetric with respect to phi. So there is a symmetry in this case. So phi disappears from this. Yeah.
Yes, I understand that, but why here you put cosine phi minus phi prime in the integral?
That's because when I start doing it from the beginning, I could, of course, have said I only calculate this for phi equal to 0 to start with. That I could have done. It will give the same results. But the calculation I do in this case, I actually calculate it for all phi's, and then the calculation shows that it is independent of phi. But I could have skipped it from the beginning because I've said from the beginning I can say I only calculate this for phi equal to 0. That I could have done too. I got the same results. But in the proper calculation, I actually need, in some ways, if I want to do it really, I need to calculate the radiation vector in this direction and this direction and this direction, which are different phi's. And then the result shows it's independent of that. Is that okay? Otherwise, think about it and bring it up at the next exercise and we can discuss it then. So if I come back to what now is the important part of this, and that is again this interpretation down here, that this is the result that we get out. And as I just mentioned to you, this is actually valid even if this is not a circular loop. It would be valid for any shape of this loop. You get the same thing. But we don't show that in this course because if you think this was complicated, the other one is super complicated. So now try to interpret this instead. If you start thinking here, we had the dipole antenna. So, you know, this pen sticking up here. And there we had that the factor that came out in the radiation vector was proportional to sine theta. So we have the same sine theta here. Same thing sits there. But in front of it, you had something that was only proportional to the length. Now it's proportional to the area. And that is the big scaling difference when you go to a loop. So instead of saying how long is your dipole, you know, compared to the wavelengths, in the loop, it's actually how big is the area compared to the wavelengths, which means that then you measure it in wavelengths. So how large is the two cross sections? And now if you start thinking a little bit, what did you know from the dipole when the dipole was small? Was it a good radiator or bad radiator? A short dipole. What happened with the radiation resistance, for example? Was it high or was it large when you looked at this Hertzian dipole, very short one? We did calculate it and figure out that it was very low. And it was basically proportional to the length of it. Now, when you have this scaling, it will be proportional to the area instead. And when you make something small, the area is, of course, the square of the length. And this says that the loop here will be extremely bad radiator. And that is what we saw in the previous picture, when you remember that before the first resonance, the radiation resistance was basically a flat curve. That is this area scaling that we actually have in these calculations. I will come back to that point too. But that is one way of interpret what comes up. If I take that one now, and we just accept what we calculated, and then we can plug it in. So we had the radiation vector. When we had the radiation vector, we removed the radial component. And by removing that, we could get the electric and magnetic fields. The radial component was already removed, by the way, in the previous one. So if I do that, then I get here the electric field. And below it here, we have the magnetic field. And you can see a few things in those. You can see the scaling again, K2A, K2A that sits there. So that is different from the dipole that's scaled as KL. So the length measured in the wave number. You can see another piece here. You can see this phase factor here. Exactly the same as we had from the dipole. If we now go back and do some thinking about that, what was the interpretation of this phase factor? We talked quite a lot about that for the dipole. There are two pieces. There is one that is 1/4 pi r, and then there is the multiplication with e raised to minus j k r. What do they quantify? Why did we get these factors that sits up there? What is the e raised to minus j k r? I can't see in this one. I should actually probably in the arguments here have an r too. I'll update it. So I have a decay with r. So the part in the phase factor, that was this time delay, the time it takes for the wave to propagate. So you ask him what is the electric field and magnetic field far away from the antenna. It takes a certain time to reach far away from it. And that is quantified by this phase factor. So it's a time delay. You take the Fourier transform, the time delay, you get e raised to that's time delay. So up there we see the time delay. And what we can see with this 4 pi r that sits down here, that is this decay of the power, the radiation intensity, how it goes down when we move away. And it's the same thing there, that if you go integrate over the sphere, the total power propagates through that one. And of course, the area gets larger, so it has to decay with 1/r2. And now the electric field is basically the square root of the power, so it's 1/r. Those are the interpretation. And then we have this donut shape, which is a sine function, sine theta, as the azimuthal angle, which says that there is less power going up high and it's more power in the horizontal plane. But there is a huge difference from the dipole, there and there. So when you had the electric dipole, what was the polarization of the electric field? It was in the
theta direction.
Yeah, and now it's in the phi direction. So we have changed those two. And in some ways, what's happening now, this is what's called a magnetic dipole. We actually interchange the electric and magnetic fields. That is in some ways what's happening. I will give you an even simpler intuition of it very soon when we'll also see the fields. So the electric field here is in the phi direction, not the theta direction. So if you think about the Earth, it sits in the center of it. That means that the electric field is east-west directed. From the dipole, it was directed now north-south. But that is the difference there. So it's 90 degrees shifted in this case. Okay, having this, we can compute the radiation intensity. Similar formula as we had for the dipole. The only difference inside of it is the factor that sets here, which is the scaling, what was the length in the dipole, and is the area for the loop. It's the only difference that comes out. So here we can then see the radiation from it. So this is an illustration in the same way as we had from a dipole. Now we have the illustration here from the loop. And what you can see there is now the electric field. You can see it's in this direction. And the magnetic field, when I look at it, is in this direction, the red one that sits there. So thinking about the picture here, now you see the loop. How can you directly understand why do you think an intuitive picture why the electric field now is in the phi direction instead? Why is that? Why isn't the electric field in the theta direction as you had from the dipole? What do you think? What is a simple way to see these things? If you think about that, you had the dipole. If you have the dipole here, so then you had some current moving in this one. And basically what you have there in the first approximation is that the electric field that sits is also pointing in the same direction. So the electric field tend to point in the same direction as the current, at least the dominant contribution of the currents. Then we have to be careful when we go out in different angles and so on. But as a first intuitive picture, the electric field goes in the same direction as the current. And if you look here, what's happening in this case is, of course, that the current moves around here. So the current is in the XY plane, which means when you look at this plane here, yeah, the electric field in that plane, as we plot here, should also be in the XY plane. So it's basically follow the same direction. And you could think about it, this is superposition, so take away half of the loop. Then that current is actually just pointing in the same way as this was a dipole. And unfortunately, on the opposite side, it will cancel that part. But it really follows the geometry where you have the current. And that means it shifts there. And that can be a good way of, like, seeing this and remembering actually what's happening with the directions of the electric and magnetic fields from a loop compared to a dipole. So this is how they look in these cases. And then if we're going to plot the radiation pattern, yeah, we can get out the directivity. Exactly the same directivity as for a Hertzian electric dipole, same thing. So 3/2 sine squared theta. So the radiation pattern here is exactly the same. There is no difference between them. But now the E and H planes, we didn't plot them for the Hertzian dipole because we didn't really need E and H planes. But when we came to the patch, we introduced them. So what was the definition of this E and H planes? That was to say that go in the direction of maximum radiation. That is anywhere down here in the XY plane. So somewhere along a line around here. So Z equal to 0. And then look at where is the electric field pointing. And the electric field was pointing in the phi hat direction. So electric field go there. Down here, the electric field goes like this. It goes around this loop. And then I can plot the E plane of this one. And the E plane then is that this is 1.5. And then it goes around here. So it's independent of the angle that sits there. The angle in this case is phi. So the angle there would be phi. That is then the E plane, because that is how the electric field is pointing when I go around this one. And if I look at the H plane instead, so let's go to the H plane that sits over here. Then I do the same thing. Then I have to go out here again, direction of maximum radiation. Where did the H plane point? It pointed in the theta direction, so that's straight down there. It is straight down there. And then I should take a plane of these ones, and then I have to cut through there. And I have to cut through on the opposite side that sits there. And that is what I get when I cut this out here. And the maximum value is 1.5. That sits in this one. So again, it's as the electric dipole, but of course now the E and H planes are interchanged in these cases. So you have to look at where is the direction, where is the polarization of the electric and magnetic fields. And of course, this one says the same thing, that, for example, if you go to 60 degrees, then you have to go up here, and then you can read off your directivity, and your directivity at 60 degrees is around 1. And the peak one is, of course, that's 90 degrees. And if you go even higher here, you go to 30 degrees, then the directivity is really low. The directivity is like 0.3 or something. So So you can just read off the intersection here with these angles, and you get out what is the directivity in that direction, which means how much power is radiating in that direction. That is what we can get out of this. So that is the patent for this dipole, or electric small loop, so the magnetic dipole in this case. And if we're going to determine the radiation resistance, we do exactly the same thing as we did with the dipole. We take the radiation intensity here, we integrate over the surface. So we take the sphere, every power that radiates out, so from 0 to pi or 0 to 2 pi, and then weight it with the phi and the theta. And of course, we need this sign part, which says that north pole is very small compared to the equator. Exactly the same calculation as for the dipole, so I don't do it in detail, and you get out some long formula that sits outside. So here we have what is the total radiated power related to the current that we send in, the loop area that sits there, and then some normalization constants of eta 0 and 2 pi. If I take that and I plug it into the radiation resistance, we have a given current, so I can compute what is the radiation resistance just from the total radiated power. And if I plug it in, I get something that looks like this. And again, in this formula here, you can see that the big scaling here is K4 A2 in these cases. And this is then in the units of ohms in these cases. So here you can see now what's happening when this gets small. When this gets small, these values that sits here are incredibly small, because if it's small, then say that it is 1/10 of a wavelength inside, it means that the area is 1/10 of a wavelength times 10th of a wavelength. And that's a much smaller number than just the original number. So the radiation resistance for these small loops is very close to 0 in these cases. So the small loop, Ka here, very small, is incredibly inefficient radiators, meaning that you need a high current to actually radiate power. So to get out powers from this one, you need a very, very strong current inside of them to radiate. And in fact, a small loop is mainly used as receiving antennas where you don't suffer as much from this. They will also be, of course, inherently mismatched to 50 ohms. And that you can live with sometimes in a receiving antenna, but not as a transmitting antenna. And they are used as receiving antennas, but not as transmitting antennas. The small loop doesn't work for this. Or it works really bad. So of course you build another antenna instead. So then we in some ways have calculated that this is very small, and that is the line that we see here. So that was this flat line here. That is precisely what we determine now, this radiation resistance. So we can see it's so small down there, so it's close to 0. The next thing that we actually can get out of this is the inductance. So the inductance is, of course, that this one here looks like a straight line. And that is that the impedance of this one is close to j omega L. The L then is the inductance for this. This is a formula that we can just, other people have derived, so I will just show that we can use it. The practical use in this case is not too high, but it can be computed that the inductance for one of these loops that goes around there is this expression. That's it. If we do that, then we can take the reactance, so the imaginary part of the inductance, omega L. We can plug it in what it is, and if I multiply this with omega, that's the same as eta 0 Ka. And if we look at the scaling here, this was Ka there, and this was normalized with eta 0, and this is now 4.7. That's what you can see there. So let's see what it is. So if this was 4.7, we can go into 1 here, then we come there, and then we have to go out here. And in my drawing, probably a little bit too high, but don't expect that I could draw a pretty straight line here, but it's pretty accurate. So the slope of the line that sits there in the reactance is really just coming from the inductance of this loop. So if you want it higher, you can have more loop next to each other and so on. And you can increase the inductance. But this small, what you say, loop antenna, it really works down here. This is where it sits. And in that case, it's basically circuit theory. It works like a circuit. These loops with many coils are, of course, incredibly popular in RFID, where you really do it as an inductance. So you put them close together, you have a mutual inductance. It's not really an antenna in that setting. And there you can use them for a lot of cases. So now we have understood some pieces of it at least. We will take a break. We will take it now actually. And after the break, then we will start to look actually at what is the comparison between the Hertzian dipoles that we did early in the course and now the dipoles, and what are the differences between them. And that is what we will use for many of these type of antennas. But let's do that after the break. So I will stop the recording.